So, as I've said before, we are taking regular languages slowly, step by step, because regular languages represent kind of the simplest kind of languages that we're going to be using. And once we do all these different things with regular languages, we will see how we can do the same things with more complicated languages, and we'll work our way up very quickly, really, once we finish doing regular languages, to talking about pretty much anything you can program on a computer. But we have one more topic we need to talk about with respect to regular languages before we move on, which is regular grammars, which is yet another way to describe regular languages. And the book assumes, when you get to the section on regular grammars, that you've already learned about grammars, which I'm not going to assume. So we're going to do a little bit of an introduction to grammars in this section, and then we will go on and talk about regular grammars in particular. So everybody's familiar with English grammar, and if you have a sentence like "the big dog chased the cat," then we can split that sentence into subject and predicate, and we can split the subject into an article, an adjective, and a noun, and so on. And there are very specific rules for English grammar. Of course, English grammar is much more complicated than the grammar of many languages, but we could say that in order to create this sentence here, what we had to do is we had to say, well, a sentence is made up of a subject followed by a predicate. And what's a subject? Well, a subject is built out of an article followed by an adjective followed by a noun, and so on, right? So we can talk about the rules of English grammar, or at least the rules for constructing sentences like this. Now, sometimes even linguists who are studying English will draw a parse tree for this kind of sentence. And so in the same way that before we said a sentence is made up of a subject and a predicate, we just draw that out using a tree structure, right? So our sentence is composed of a subject and a predicate. Our subject consists of an article, an adjective, and a noun. And eventually we get to kind of the leaves of our tree, which are the actual words that we're using. So if you look at this, all of the leaves on the tree are words in the English language, and the internal nodes on the tree are parts of speech. Okay? Or grammatical predicate isn't a part of speech, is it? My English grammar is not fantastic. So grammarian terms, we'll call it, or something. But the important thing to note here is you start with your sentence, you break down into the different parts, and all of the internal nodes in the tree are kind of in one class of things, and the terminal nodes of the tree, right, the leaves of the tree, are all actual words in the English language. So now let's talk about the grammar for an arbitrary language, keeping in mind that now by use of the word language, I mean a set of strings, right? If I say to you, at least for the rest of this semester, what's a language, you should just instantly blurt out at this point, it's a set of strings, okay? So if we have L as a language over an alphabet A, then we can talk about a grammar for L, which is a bunch of grammar rules, right? And they all take this form. And the form is one thing, arrows, another thing, okay? So in this case, we've got gamma arrowing delta, right? So, and we say gamma and delta in this case are strings of symbols, and these symbols are in my alphabet A and also from my grammar symbols, which are disjoint from A. So this is the formal definition of a language. Let me show you what I mean. I think when you see this example, it'll make sense to you. So let's let A be the alphabet consisting of the symbols A, B, and C. And we're going to say S is our start symbol. So here's a grammar for A star, keeping in mind that A star, remember, is the set of all strings over this alphabet, right? So anything we can come up with. So when you start, you either end up with lambda, or you end up with A followed by something made up of S, B followed by something made up of S, C followed by something made up of S. Let's look let's try and derive the string CCAB, right? And then you'll see what's going on here. So what I can do is I can say, well, if I start with S, you always start with your start symbol. From S, using this last rule here, I can derive, and we're going to use this double arrow, CS, right? So effectively, I took this single S and expanded it using one of the rules into CS, right? And now from that one, I'm going to expand that into CCS, because again, what I did is I took this single S and I turned this single S into CS using this last rule. Okay. I think what I'm going to do is shrink this a little bit so I have a little bit more room. Let's get that up there, and we'll take this and move it over here. Okay. And so remember, I'm trying to derive CCAB. So now I think you know where we're going here. I'm going to do CCAS because, of course, what did I do? I took this S and I expanded it into an AS using this second rule here, right? And still I don't have enough room, so bear with me. I'm going to do a symbol that is not really part of grammar symbols, but you'll get it. All right, so we'll arrow up to there, and we'll expand that last S into a BS, like so. CCAS, oops, CCABS, because this S is going to expand into BS. Notice, by the way, the stuff I'm writing in red here is not part of my derivation. I'm just trying to show you what kind of gets expanded. And we're not quite done yet because we still have this capital letter S in here. And the things on the left-hand side of this grammar, which in this case are all just S's, we call non-terminals. They're like the internal nodes on our tree. They're not part of our alphabet, so we can't stop there. So what I'm going to do is I am going to say, well, that one goes to CCAB lambda, because of course we can take S and turn it into lambda using this rule up here. And so now if you look, I've derived CCAB lambda, but CCAB lambda is exactly the same as CCAB, right? And so I have derived CCAB using these rules. Here's a cleaner version of what we just did together as a group, and you'll notice that in here I tell you that this arrow means derives in exactly one step. So this these lines like you know, S goes to BS, that's called a grammar rule or a production rule. And when we're talking about in here, if we have gamma arrows delta, we can say gamma produces delta, or replace gamma by delta, or gamma rewrites delta, or gamma reduces to delta. And in fact, you've heard me already informally, it's not so accepted, but I'll say something like gamma goes to delta, or gamma, I often say expands to delta, even though reduces to is the more polite way to say it, the more official way to say it. So in here I would say S produces BS, or S reduces to BS, or one of these. And so just like a DFA or an NFA always has to have a start node, Every grammar has to have a special grammar symbol called the start symbol. And you have to have at least one production rule. This is one production rule, but there must be at least one production rule that only has a start symbol on the left-hand side. You can have just one, or you can have more than one. And as we've seen in our grammars before, we had the start symbol on the left-hand side in several production rules. And you know, you've probably figured out that you can have a parse tree for these kinds of derivations too, right? So if we say we start with S, we get this S up here, that reduces to AS, right? And so you can see we have the parse tree for our AS, and then and that's just kind of showing you that this piece S goes to the AS, and then this piece S here, right? So that S on the right here actually reduces to BS, and so on. Okay, here's the formal rules, the formal definition of a grammar. Some of this will make more sense as you see more grammars. But a grammar is going to have a finite set of grammar symbols that are called non-terminals. These non-terminals are basically the things that are not in the alphabet, right? And they are also on the left-hand side. I'm writing LHS for left-hand side of my rules. Okay, that's the non-terminals. They may appear on the right-hand side too, right? But definitely on the left-hand side. We also have a finite set of symbols called terminals. These are going to be the letters in our alphabet that we're using in our language. And our non-terminals and terminals have nothing in common. One of our non-terminals will be called the start symbol. It doesn't always have to be the letter S, though we will often use the letter S. And then we need a set of production rules. Notice that we say finite. You can't have an infinite set of production rules. And they take the form that we've seen, where it's gamma arrow delta. And effectively, what this stuff down here is saying is, look, gamma, the thing on the left, can't be empty. You've got to have at least one rule that has S by itself on the left-hand side. And all of the non-terminals have to be on the left-hand side of some production. So the non-terminals have to be on the left-hand side. They have to be expandable. Again, let's look at some more specific examples. It'll probably clear this up, and you can come back and look at this slide again in a couple minutes. Just one point of clarification. We have always said that lambda can never be part of an alphabet. Okay, and we're going to continue to say that lambda is the empty string. It's a special character. You are not going to find it in any alphabet. But just to be clear, in order for us to be consistent with the book, we're going to say that if lambda is a part of a grammar, then it's one of the symbols in the set of terminals. Okay, so generally our terminals are just letters of the alphabet, but it may also, our terminals may also include lambda. All right, so just this final line will continue to say that lambda is not a part of our alphabet from which we take symbols for our strings in our languages, but can be one of the symbols in our set of terminals. Now, it is possible for a grammar to have more than one non-terminal on the left-hand side, and there's nothing about our rules for grammars that say that you can't have terminals on the left-hand side as well. But for the purposes of this class and for everything that we're going to be doing, we are only going to have a single non-terminal on the left-hand side. So that's kind of note 1. And note 2 is, you know, computer scientists like shortcuts, and mathematicians like shortcuts too. And so what we're going to do is, if we have a bunch of rules that have the same non-terminal on the left side, so for example, excuse me, all of these rules have the non-terminal s on the left-hand side, right? We can combine these rules by just saying s goes to lambda or as or bs or cs, right? And here we go again. We're using this bar symbol to represent yet another thing, right? We've used bar symbol in our sets to say x such that x is less than 5. We've used the bar symbol to talk about the size of a set, right? We've used the bar symbol for a bunch of things. And now we are also using it as our divider for these rules. And sorry, you just need to be able to kind of tell the difference from context. So now we just need to talk about how do you build a grammar, right? And so, you know, how do you use your wits to make a grammar? And it's just to kind of, you know, how do you think about building these things up? So let's just talk about this, and let's do a few examples. So this first example, and I'm just going to give you the production rules. I'm not going to give you the 4 tuples. So let's look at this first one. We need to find a grammar for the language a to the n such that n is an element of n, right? That's the same as saying we're finding a grammar for a star, which we've done before. It's you've probably remember how to do this one, but we're just going to say, well, you're going to start, and either you're going to go to an a followed by the start symbol again, or you'll go to lambda. Yeah, it's pretty easy, right? Because we just keep kind of building up the a's. This next one, a to the n, b to the n, right? So 0 or more a's and b's, right? So 3 a's, then 3 b's, or 27 a's and 27 b's, or lambda, the empty string, right? And in fact, no, this is not a regular grammar. But just because it's not a regular grammar, remember, we're not doing regular languages right now. We're just doing, we're not doing regular grammars right now. We're just doing grammars. And so, so we can do a grammar for this. It will not be a regular grammar because our language is not a regular language. But that's okay. So when you're doing something like this, a to the n, b to the n, you need to kind of think about how you build it up. The important thing is every time you add a as a non-terminal, you have to add b as a non-terminal. And what we can't do is we can't do something like this. We can't say s goes to abs. As a production rule, because then we could get something like s goes to abs, goes to abs, which would mix up the order of our a's and b's, right? And here it's all the a's come first, then all the b's, right? A to the n, b to the n. So that's no good, right? So we can't do that. So let's get rid of that and try again. Okay. So what we're going to do is we need to have the same number of a's and b's, but we need them to kind of bubble out from the middle, right? So our rule is going to look something like this. We're going to say s goes to ASB, right? So every time we put that s in, the a's are on the left and the b's are on the right, or lambda. And if you look at that, then if I'm trying to derive a string like AABB, you'll see what we get is we get something like S goes to ASB, goes to AASBB, goes to AA lambda BB. And we got it. So that's pretty good. Okay. Finally, let's do this last one. Now we want AB to the n, right? The language AB to the n, and that is in fact a regular language, right? So it's just a bunch of ABs, 0 or more ABs. And that was in fact what I wrote in red before, right? So we're going to say S goes to ABS or lambda, right? So every time we put in our letters, we'll put in our ABs, and then we could expand some more if we wanted. I don't expect that finding these three languages for this first slide would be easy for you. It does take a little bit of practice to understand how these things work. I think what you need to kind of really look at and really note here is the difference between how these three grammars work, right? So this first one, it's just a single letter building it up. It's pretty easy. And in fact, you know, you might want to note that we could also have had said this goes, S goes to SA or lambda, right? Nothing wrong with that. And similarly for this last one, we could have said S goes to SAB or lambda. That would have been fine. But this middle one, where we really need to kind of build it up from the middle, it's almost like I keep thinking of it bubbling out of the middle. It's really important that we get that S in the middle. We're expanding from the middle. But the good news is we're not going to have to do that kind of weird bubbling out just yet, because the language A to the N, B to the N is not regular, and those bubbling out languages are not regular. And for now, we're going to talk about regular grammars and what makes a grammar a regular grammar. So here is the formal definition of a regular grammar. We say that a grammar is regular, or it's a regular grammar, if all of our production rules look something like this, where the capital letters are non-terminals and this omega is some non-empty string of terminals. Okay, so we can have a non-terminal going to lambda. We can have a non-terminal going to this omega, some string, right, non-empty string. We can also have a production rule that has a non-terminal going to another non-terminal, right? And we can have a production rule that says we have a non-terminal going to a non-empty string of terminals followed by a non-terminal. So what's special about this that makes it a regular grammar and not just any old grammar, right? There's two key things here. The first is that there's only one non-terminal on the right-hand side, right? So if you look at these, you can have a string of terminals, right? But all of these rules, the only ones that have a non-terminal on the right-hand side are the last two, right? Sorry, and yes, they're the only ones that have a non-terminal on the right-hand side. And furthermore, there's only ever one non-terminal on the right-hand side when there is one. And in addition, if there is a non-terminal and there are any terminals in there, the non-terminal has to be to the far right, right? So if you look here, there's either a non-terminal by itself or a non-terminal that's at the very end, right after the string of terminals, right? The non-empty string of terminals. So this means we can't do that bubbling out trick that we've been doing for making those languages that aren't regular. Okay, so we've talked about these rules that tell you what makes a grammar a regular grammar. Let's look at these examples and see which of these are regular. Well, this first one is not regular because it's got that B in the middle there, right? That capital B, a non-terminal, which is not at the far right of the right-hand side of that production rule. Okay? Let's look at the second one here. Again, it is not a regular grammar, right? It's not a production rule that could be part of a regular grammar because we have two non-terminals there, right? And you can't have two non-terminals in a on the right-hand side or on the left-hand side, for that matter, of a regular grammar of a production rule. This last one, however, looks good. What have we got? We've got a string of terminals followed by a non-terminal, which is just this form. So that's a production rule that's that is of a form that could be part of a regular grammar. Now, one thing I just want to clarify about this last rule here is it's okay for to have something of the form S goes to, say, AS. There's nothing in our rules that says that S and T cannot be the same non-terminal. Our rules just say that S and T have to be non-terminals. So don't be stressed out if you see something like that. That's also part of a regular grammar. Right? And you'll notice that in this example we just did, we have A on the left-hand side and A on the right-hand side as non-terminals. That's okay. There's nothing in our rules, go back a slide, nothing said that S and T cannot be the same non-terminal, right? So this is perfectly legal. Now, it is really important to note that grammars are not unique, right? You can have two different grammars for the same language. We've seen that before, right? And there can be two different regular grammars for the same language too. You shouldn't be surprised by this, right? While we said that there is one minimal state DFA, right? We know that there's a ton of DFAs that recognize the same language, right? So for example, if we look again at that DFA that we had before for A star B, right? Here was our DFA for A star B. We had our start, and we had A looping, and B going to state 2, and then we had our kind of garbage state over here, which had an A, B loop, and that was A, B. So that's that's a minimal state DFA. But what if I added state 4 here, and I said state 4 looks like that. That's another DFA, recognizes the same language, right? Just because you can't get to 4 doesn't mean that you can't have it, right? I mean, you could have, there's state 5, which just loops on itself. Still, all 5 of these states, that's a totally valid DFA. There's nothing that says all our states need to be connected. So that's a completely valid DFA that recognizes the language A star B. So just because there's a single unique minimal state DFA doesn't mean that there's a unique DFA. There's a ton of DFAs. Actually, more than a ton, an infinite number, right? We can keep adding nodes as long as we want to. So let me squidge that down and make this one back to full size. So, you know, we can have two different NFAs for the same language. We can have two different DFAs for the same language. There can be multiple regular expressions for the same language, right? So another regular expression for A star B is B plus A star B, right? So you can have a B on its own, or an A followed by 0 or more A's followed by a B. I mean, that's a regular expression. Another regular expression for the same language is just B plus A star B, right? Because it doesn't make a difference if we repeat something, right? These are all perfectly reasonable. And the whole point of this slide is just to tell you that grammars are not unique. There can be two different grammars for the same language, so don't get stuck on that. There can be two different grammars for the same language, and there can be two different regular grammars for the same language as well. So let's see what happens. Does this shrink everybody now? Yeah. Woohoo! So let me just show you two grammars for the regular expression A star B. Okay? Here's one grammar, a regular grammar for A star B, which would be S goes to AS, and S goes to B, right? So as many A's as you want, and then you end with a B. And of course, this language, these production rules here that I've just circled, that's exactly the same as saying it in one line, right? S goes to AS or B, just to remind you we can do it in one line. But we can do this same rule, let's change colors. We can do this same, we can do this same grammar, so we can represent the language A star B with a different grammar, we could say that S goes to AS or AAS or B, right? It's certainly a different grammar, different production rules, right? This one has 3 production rules. The previous one has 2 production rules. The purple one has 2 production rules. And this just says you get to choose when you add your A's. You can add 1 A at a time. You can add 2 A's at a time. Both of them represent the language A star B. And my reminder was ahead of time. Just remember that this notation here is just a shorthand, right? Computer scientists like shorthands. Apparently people who write books about discrete math like using this bar symbol to represent everything from size of to our such that, you know, in a set x such that blah blah blah. So other than the fact that we use that bar symbol for just about everything we can think of, it's important to remember that we're just using a shorthand here. If you have a rule that looks like that, oops, I'm not circling it very well, you just want to think in your head, oh, that's shorthand for these 3 rules, right? Just remember that. Now, there are some things that can be very difficult when you are trying to work with regular grammars. For example, suppose that you have a grammar for A star. Here's a grammar for A star. It's pretty easy, right? It's a regular grammar where A is my start symbol, and there's just 2 rules. A goes to little a big A, or A goes to lambda. And I can have a similar grammar for B star. It's just B goes to little b big B, or another rule, B goes to lambda, right? Individually, these are pretty easy. But I can't just squish things together if I want to figure out A star, the language for A star, B star, right? I mean, it would be really nice if I could just say, well, S goes to the A part followed by the B part, and here's what my A part of my language is, and here's what my B part of my language is. But of course, if you look at this first rule, S can't go to AB because these are both non-terminals, and a regular language has to have only one non-terminal on the right-hand side. But we know that A star, B star is a regular language, so there's going to be a regular grammar for it. We're just going to have to look harder to find it. So you may want to pause this video for a minute just to see if you can figure out a regular grammar for A star, B star. My hint is work on it from left to right, but now let me just show you. So here's my regular grammar for A star, B star. I'm going to say that A goes to little a big A or B, where B is another non-terminal, right? That represents 2 production rules, both of which meet the rules for regular grammars. I'm going to say B goes to little b big B or lambda. So that's a pair of production rules. No, I'm sorry, that's 4 production rules, right? Because these ones actually expand. These are shorthand. But I believe that these 4 production rules will generate the language A star, B star, right? But it is a regular grammar, not, well, it is a regular grammar and a general grammar, whereas the previous grammar we were looking at wasn't regular. I'm also going to point out that for this example, I wanted to start with something that was not S, because we're always starting with S. And I wanted to show you an example of something that doesn't start with S. Remember, our rule is that the first production on top is the one that you start with. So in this case, if we were to expand these rules, it really is A goes to little a big A goes to B goes to little b big B, B goes to lambda. So if we just give the production rules and we're not actually giving the full 4-tuple for our grammar, we say that our start symbol for this grammar is A, right? Because A appears here on the left side of the first rule. So here's another regular grammar problem. We want to find a regular grammar for the language A star, B, C star, D. Again, you know, my hint is just to work from left to right. It's very similar to what we did before. You may want to pause the video and try and figure it out. I'm going to do it for you right now. So let's see, I'm going to start with S for a change, or to get back to normal, and I'm going to say, let's see, S can be little as, or it can go to, and what I'm going to do is I'm just going to say it can go to the rest of this stuff, right? And I'm going to call the rest of this stuff B, right? And the rest of this stuff is just B, and I guess B is going to go to a little b followed by a c, where I'll call C this rest of the stuff. And to do the C part, well, now I'm just trying to do C star D, so C goes to little c, big C, or we could end with a D, right? All right, here's some regular grammar problems from the book. Find a regular grammar for each of the following regular expressions. So let's see if I circle these. So we'll start with A plus BC. Again, consider pausing the video and doing all of these, or pause the video in between them so that you get some practice. But for A plus BC, I'm just going to say S goes to A or BC. Trivial, right? The next one is AB star plus C. So one option is S could just go to C, right? The other option is S could go to an A followed by the rest of it, which I guess I'll call A. And that A rule is going to have to represent my B star part, so I'm going to say A goes to, let's see, it could go to a BA or lambda. All right, so that's that stuff. Let's pick another color. I don't have that many good colors in here, unfortunately. Let's do the next one in black. So now what I'm going to do is I'm going to do this language here. Oops, I just overwrote it. Which is A star BC plus AC. So let's see. For starters, I could just say S goes to AC, right? Because that's the easy one. And now I need to do the rule for A star BC, so S goes to AS or B. And let's see. And in fact, I could write S goes to AS or little b, big B if I'm feeling lazy, right? And then big B goes to C, big B, or lambda. I think that does that one. And we'll do the last one in red. Ooh, there's a concatenation. So you got to start with an AA or a BB. And then you have to end with AA or BB star. I see. So for this one, it's you have to have at least one AA or a BB, and then as many more of them as you like, right? But you can flip back and forth between them. So this one's a little tricky. Even if you didn't pause for the other ones, pause for a minute. So let's see. Instead of starting with S, let's start with Q for a change. So Q could go to AAQ or BBQ. And really, that's going to give us as many pairs of A's or pairs of B's as we want. Because remember, what do we got here? We have, you have to have at least one AA or one BB, and then you follow that with 0 or more of whichever you like. So the trick here is going to be ending. We can't say Q goes to lambda, right, as another rule, because that would mean that that lambda would be in our language, right? We can't have lambda in our language, so that's not a rule we can have. So what we need to do here is we need to say, when you're kind of done with making as many extras as you want, make sure that Q goes to either an AA or a BB. And again, let me just remind you that all of this stuff, this is actually 4 production rules, right? So my production rules for this are Q goes to AAQ, Q goes to BBQ, Q goes to AA, and Q goes to BB. So this thing in here, just a shorthand for these rules. All right, some more problems from the book. Find a regular grammar for each of these. So we'll start with purple. This one's easy, right? This is just a finite number of strings, right? So we could say, you know, maybe I'll start with A here, and I'll say A goes to AA or AB or AC. The next one, let's see, what have we got? We have, it looks like what we have here is odd numbers of A's, right? So you can have 1, 3, 5, or A to the 2n plus 1. So if n was 3, let's see, if n is 0, then it's A to the 1. If n is 1, it's A to the 3. If n is 2, it's A to the 5, right? So this is kind of odd numbers of A's, right? So let's think about how we would do that. In fact, pause the video for a minute. Think about how you do that. And the way I think about this one is it seems to me that you have to kind of always put down pairs of A's until the end when you have to put down a single A. So I'm going to have this set of production rules start with B, just because I want to show you that production rules can start with whatever the heck you want. So I'm going to say it could go to 2 A's followed by a B, or just a single A. And I think if you look at that, you'll see that that'll generate our whole language. This next one, its bark is actually worse than its bite. It looks kind of nasty, right? It's A to the n union B to the n union C to the n, right? The regular expression for this would be A star plus B star plus C star, right? And you should be able to do that in your head, right? You should be able to look at this and say, oh yeah, that's what this is. So what I'm going to do, let's start with capital D now. I'm just skipping C because lowercase c and uppercase c is hard to distinguish sometimes. So, so I'm going to do it with, I'm going to have my first production rule start with D. And what I'm going to do is I'm just going to, since this is 3 different sets of strings we need to generate, I'm going to say D goes to E or F or G. Now remember, that's perfectly legal, that's regular, because this is actually a shorthand for 3 different production rules, right? And now, it's not too bad, right? E is going to be my A, so E goes to AE or lambda, and F goes to BF or lambda, and G goes to CG or lambda. Okay? And so now we just have to do that last one. I guess we'll switch back to purple again. So we're doing this last one. A to the 2k such that k is an element of n, unioned with B to the 2k plus 1 such that k is an element of n. Ouch, right? So what have we got here? Think about it for a minute. Pause for a second and think about what is the regular expression, right? What have we got here? So on the left, this piece here on the left is pairs of A's, right? So it's going to be AA star. And the one on the right is odd numbers of B's. So, you know, k starts at 0, and then we have 1 B. Or k is, if k is 1, then we have 3 B's. So I'm going to say it is BB star B, right? And so again, let's see, we were up to G. So let's start this set of production rules with H. And I'm going to take each of these two sides in turn. We'll start with this left one. I is a weird capital letter too, so we'll go to J or K. And we'll do that AA star for the J part. So J is going to go to pairs of A's followed by a J or lambda. And K, which is the other one, is going to go to pairs of B's followed by a K, or in this case not lambda, but we end with a B, so we get that odd number. And finally, we have some even more tricky problems from the book, right? So find a regular grammar for each of the following languages over the alphabet A, B. So strings that have a length that is a multiple of 3, and strings that have an odd number of A's. So pause the video and think about the first one for a minute. We'll do the first one in purple. So pause the video for a minute, think about it. So it helps me to think about the regular expression that represents these things. And a length that's a multiple of 3 means that we're going to have to put down chunks of A's and B's where there are 3 of them. And the easiest way that I can think of for a chunk of A's and B's with 3 is to just kind of list them all out. So we got AAA, or AAB, or ABA, or ABB, or BAA, or, wow, there's a lot of these, huh? BAB, or BBA, or BBB. Did we get them all? It should be 2 cubed, which is 8, right? Because there's 2 possibilities for each space. So 1, 2, 3, 4, 5, 6, 7, 8. Woohoo! I think we got them all. So that's the a regular expression if we just wanted one triple of letters, but I want multiples of triples of letters, right? And 0 is also multiple, so I want 0 or more of these. And so the regular expression I'm going to use, and just pretend this is all on one line, all right? Is this thing starred, right? So so how do we do that as a grammar? Well, it's going to be messy, but it's okay. We could say something like S goes to AAAS, or AABS, or ABAS, or ABBS. Let's start again. S goes to BAAS, or BABS, or BBAS, or BBBS. And that gives us the as many as we want, and then we just have to add an or lambda so that we can stop, right? And we have a string when we're done, and also we can have lambda, right? Because lambda is a length that's a multiple of 3, I think. So it's a bit ambiguous, isn't it? I suppose you could argue that it's not a multiple of 3. If you don't think 0 is a multiple of 3, then what you would have to do is you would have to say, all right, scratch that lambda, and I have to end with one of these guys again, so AAA, or AAB, or ABA, or ABB, or BAA, or BAB, or BBA, or BBB. I fit them all in. So you decide. If the language we're talking about is this one that I wrote up here, this regular expression with the star, then you want to get rid of this last line and include lambda. And if you want to have multiples of 3 where there's at least, 3 there, you're starting with 3, then you get rid of lambda and you include all that stuff. Okay, so that's the first one. Now let's see if I can shrink that. Actually, I think it's messy enough that I'm just going to erase it all. Bear with me. Oops. Now we got to erase this piece. There we go, very good. Okay, so now let's do in blue all strings that have an odd number of A's. And again, pause this for a second. So this is over the alphabet A, B, remember. So we can have as many B's as we want, but whenever we have an A, it's got to be an odd number of A's. So this one's a little bit weird. It would be, I don't know if it would actually be easier if we were trying to do a grammar that wasn't a regular grammar. But here's what I'm going to think about it. We have to build the string up somehow, right? And at any point in time, that string is going to either have an even number of A's or an odd number of A's. And I'm only going to stop when I get an odd number of A's. Okay? When I can only let myself stop generating the string when I have an odd number of A's. So what I'm going to do is I'm going to say that we can start when we have our first production rule. 0 is even, right? So we're going to start, I'm going to have two production rules that I'm going to, let me put it up here in the corner just so I'll do it in green. I'm going to have E represent, I currently have an even number of A's in my string. And I'm going to have D, because I don't like using O as a production rule as a capital letter, to represent I have an odd, right, number of A's. So if I start, I can either start with an A and immediately go into my deal with the fact that I have an odd number of A's now, or I can go straight to the even rule because I have an even number of A's. So if I have an odd number of A's, I have two choices. One, well, let's see, I have several choices actually. One is I could stop, right? I could just throw in a lambda because I have an odd number of A's. Another option is I could add in as many B's as I want, right? Because nobody said anything about the B's. And finally, if I want to add in an A, that's totally fine, but then I kind of go to the world where I now have an even number of A's. And so now we just need to finish off. If I have an even number of A's, I can add B's if I want, right? Or I can add a single A and say now I have an odd number of A's, and so I go back to that kind of odd generating rule. But I can't add the lambda here because I don't want to end with an even number of A's. So I think that's my answer. So again, go away, practice generating these grammars, more problems from the book, more problems that you make up yourself, more problems that other people suggest. Okay, and of course all the homework problems. But that's it for regular grammars. There's not a whole lot to them once you know the rules.